So I'll record these again now that I had to send an email asking for permission. So last class I didn't record, but I'll start recording all of them in the future. And they'll be basically this with a bunch of cats behind me, probably. There's one sleeping up there. Or I've got the YouTube videos which talk about roughly the same topics, pretty well identically the same topics. So last time we were doing electric charge density, and I was going to do the example of electric charge density over rectangle R, which was 0, 2 cross 1, 2, is given by sigma of x and y. So at each point, this will be x squared plus 3y squared. What we want to do is find the total charge Q over R. So the first thing we should do is draw our region, just in case we have to find out if it's more complicated, whether we want to use rectangular coordinates and just Fubini's, or whether we have to use general regions of type 1 or type 2, or we might want to convert it to polar as well. Depending on what we want to do with this, we definitely want to draw our picture, and it will help us decide. Our rectangle is, let's just make some coordinate axes. So this is going to be x is from 0 to 2, and y is from 1 to 2. So this will be our rectangle, R, and that tells us, of course, we have technically type 1 or 2, because they're all constants, it doesn't matter. And so we're integrating over this, and it tells us that our sigma of xy is x squared plus 3y squared. If we do this, total charge density is just like mass density. The total charge density is just the double integral of either the mass density that they give you rho or the charge density sigma. So in our case, the total charge density Q is equal to the double integral over the rectangle of our charge density, dy dx, or dA you can call it, I guess. Why does that do that? And that, because we set it up ahead of time, we now know what our region is and how to describe our region. So this will equal the integral from 0 to 2, the integral from 1 to 2 of x squared plus 3y squared dy dx. I like to do dy, stick to my guns and do dy first, always if I can. This will equal the integral from 0 to 2 of, I'm taking the antiderivative, so x squared y plus y cubed, meow meow. There's a cat meowing in the background, from 1 to 2 dx. This equals the integral from 0 to 2 of, I put 2 in there, so I'm going to get 2x squared plus 8 minus, I put 1 in, I get x squared plus 1 dx. Simplifying this, I'm going to get the integral from 0 to 2 of x squared plus 7 dx. Once I compute this, now I take the antiderivative with respect to x. I'll get, by the fundamental theorem of calculus, part 2, I'm going to get 1/3 x cubed plus 7x, evaluated from 0 to 2, which is going to give me 8 over 3 plus 14, which is 8 over 3 plus, I'm going to multiply by 3 over 3, so 42. Some number, 50 over 3. charges usually in coulombs. I'm not too interested, but the physicists are interested in this. I just want to do the mathematical calculations of doing double integrals and applications. Where's another one? Let's do, let's see. Okay. Let's do one more electric charge density and then we can move on. So let's call that example 1, I guess, for today. Example 2. So let's do electric charge density over, now let's do the unit disk. Which we mean by x squared plus y squared is less than or equal to 1. So everything inside the circle, the solid region in there, is given by sigma of xy is, what do I want? 1 plus x squared plus y squared this time. So again, I'm keeping these fairly simple so that we can focus on the new double integrals and applications of double integrals, but also integration can get crazy. So we'll eventually do some that have more complicated integration techniques. Find total charge Q. So in this region, what we have is the unit circle. And so the best way probably to do this, if we're going to do this, we could write this as in Cartesian. Type 1. I can write this as -1 is less than or equal to x. X goes from -1 to 1. And then when I'm trying to do the y values, where does y go from now? Y goes from here to here. And this one is negative the square root of 1 minus x squared, the bottom half. And the top half is positive that guy. And so that doesn't look very nice. Instead, what we can do is write this in polar. What we're going to have is, if we redescribe this, we have 0 is less than or equal to theta is less than or equal to 2 pi, 1 full revolution around the circle, and then we just have 0 is less than or equal to r is less than or equal to 1. So we have a horrible type 2 or type 1 region in the general sense if we use Cartesian, or we just have basically Fubini's in polar coordinates where we have constants and everything. So I would like to use this, and then remember that we have x squared plus y squared equals r squared is the conversions, and then we know x is r sine theta, or r cos theta, and y is r sine theta. Therefore, this says that our total charge Q over this region is the double integral over our region R of sigma xy dA. Because this time we drew our picture or and decided we want to use polar. This is going to be the integral from 0 to 2 pi, the integral from 0 to 1 of when we convert our function, 1 plus x squared plus y squared equals 1 plus r squared. So that's our sigma. So this will be 1 plus r squared. And then don't forget we have r d theta as the difference when we do this polar differential. You can, of course, split this. This is the integral from 0 to 2 pi d theta times the integral from 0 to 1 of 1 plus, let's just distribute that in there, r plus r cubed dr. Once I have this, I can just compute these integrals separately. The integrals separately are going to be theta evaluated from 0 to 2 pi times 1/2 r squared plus 1/4 r to the 4 from 0 to 1. This gives us 2 pi minus 0 multiplied by, what am I going to get, 1/2 plus 1/4 minus 0. So this now gives me 2 pi plus 3 over 4, which is going to be equal to 3 pi over 2. Again, coulombs, I guess. Our third application, application 3, is going to be moments in center of mass in 2 dimensions, and then we'll do it in 3 dimensions and we'll get triple integrals. 4. So I'll describe the one-dimensional scenario just to get us to remind us what we mean by center of mass, etc. And then I will do this for the center of mass of lamina or planar regions, just like we did for the mass and density. So starting off with the one-dimensional case, what we're going to look at is, it's going to be like the lever principle, which Archimedes comes up with, I believe. He says, give me a lever long enough and I can move the world, and a place to put it. But what we're going to do is, if we have 2 masses, say mass 1 and mass 2, so we're going to have an m1 and an m2. So this is just 2 masses in 1 dimension. We're just talking about the horizontal movement of this. Basically, what we're going to have to do is, what we cleverly do is put a coordinate axis on there, is what we're going to actually do. So then this will be, we put one of them at 0, or sorry, this doesn't have to be at 0 necessarily. We're going to put a coordinate axis, and then so we're going to measure out, and this will be x1, our position x1 in the horizontal, and this is our position x2 in the horizontal. So there's only 1 dimension that we're considering with this scenario. And then there would be, at some point, we're trying to find where we would put the lever so that this would balance off and we could have complete equilibrial rest where this wouldn't tilt. Like the pen, if I could take the pen and like balance it somewhere, it's like, oh, there's going to be a center mass of this end's heavier, is this end heavier? It's like, well, we got to find where it sits and rests. Wherever it sits and rests, we found the center. Oh, I didn't have it up there. Before, when it wasn't working, it's like, oh, that's not the center of mass. When you find the center of mass, it's like, where is it? It's right there. When it sits and rests, that's this. It has to be the center of mass of the pen, even though there's more mass on this end than there is on this end, because this end's empty. So that's what we're finding. When we do that, now this is what we're going to call X bar, this location. And this guy in here, we're going to call D1, and this one we're going to call D2, distance 1 and distance 2. So what the lever principle tells us is that to balance this, there's a point where D1 M1 has to equal D2 M2. or we get that d1 has to equal x bar minus x1, and d2 has to equal x2 minus x bar. From this, we can conclude that m1 x bar minus x1 has to equal m2 x2 minus x bar. And if we solve, in this case, solve for x bar, I won't do all the steps, but immediately flip it around, and you're going to get that x bar has to equal d1 m1 plus d2 m2 over m1 plus m2. This is called center of mass in one dimension. We also call d1 and times m1 and d2 times m2 are called moments of mass. So it's the moments of mass divided by the sum of the masses is the center of mass. Why do I do that? Because it'll make a little bit more sense now when we jump to the two-dimensional scenario. In 2 dimensions, we're going to have a similar scenario. We're going to have, let's draw a picture, and then we're going to have an arbitrary region, R. And so for every point in there, we're going to have essentially, let's use, there's going to be somewhere, I don't know if that's going to be it, but where there's going to be an X bar, Y bar, where we want the center of mass. So first of all, we're going to have capital M, which is equal to the sum from I equals 1 to n now of DI-MI. That's going to be this big M. In this case, we would call this in the one-dimensional case, we would just call it the sum of the first two. But what we're going to call this is this is the moment of the system. And so what we're really going to do is we're going to do the moments of mass with respect to the axes. With respect to the x-axis, first of all, and y-axis are given by, let's do it this way. Let me redraw this by, let me draw this picture. So if I have something that encapsulates the x and y axis, what we're going to do at every value, use pink here. So here, if I go out to a value of this point, and then here to say here, to here. If we look at this, then we add all these up, we're going to have, this will be x3, y3, x2, y2, and say x1, y1, we're going to have a bunch of points. Just x, y. Right. So what are we going to do with this? What we're trying to do is we're trying to balance out the weight of everything or the mass of everything with respect to the y-axis and then with respect to the x-axis. So the first one, what we're going to do is moment of mass with respect to the x-axis is going to be denoted mx, and unfortunately that's going to have the y in the formula. This will be the double integral over our region D of y times the density at each point dA. Again, you don't have to know a bunch about the physics. Basically, you have to know that the formula is going to be this. The moment of mass with respect to the x-axis is going to be, unfortunately, denoted mx, but if you want, you can say x-axis, or that's y equals 0, which helps us. So because it's the y equals 0 equation, it's going to be y rho xy. The moment of mass with respect to the y-axis, or that's going to be when x equals 0, is going to be what? Unfortunately, we call it my because it's with respect to the y-axis going across the y-axis or the x-axis, but this gives us a double integral over the region D of x times the density rho xy dA. And then recall the mass is given by m, which is just the double integral of the density at each point, the variable density. And then finally, we combine the ratios of these three things to give us center of mass. The center of mass, denoted x bar, y bar, is given by x bar is equal to my over the mass, which is, recall now, going to be my is the double integral over the region D of x rho x y dA. So if you want, I would get rid of the my part. Just remember that x bar is equal to the double integral of x rho x over the double integral of just rho xy. That's x bar. And y bar is going to be what? Mx, the moment with respect to the x-axis, the y changing over the x-axis over the mass, which is the double integral over the region D of y rho xy dA, all over the mass, which is the double integral over our region D of just rho xy. So that is the center of mass in 2 dimensions. In 3 dimensions, it gets more complicated. We have moments about the xy plane, the xz plane, and the yz plane. So let's do example 3. No questions so far. So yeah, this is basically, I said the applications would be more in the physics type region, and then when we do 3 dimensions, we can have uh, similar type versions just for the 3-dimensional solids that we have instead of the 2-dimensional objects. So let's find the center of mass x bar, y bar of the region D, which is now a general region bounded by the parabola y equals 9 minus x squared, and the x-axis, if our density varying at every point is just equal to the value of the y coordinate. So what are we doing? Again, we want to draw a region and draw a picture, which is frustrating at first, but the more complicated it gets, the harder these are to do. But you want to ground yourself and see if everything lines up and makes sense. What we're going to do first of all is, oh, I should probably draw a tall one. But we have 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have, it says bounded by the parabola 9 minus x squared and the x-axis, which is y equals 0. So where does it have zeros? At -3 and 3, and so it's the upside down parabola. Oh, I missed. I missed again. Oh, doesn't want to draw that half for me. I'll get it. It's because my hand has this weird bump on it. Oh, I erased everything. Way to go. The first one was good. Close enough. No, not close enough. Why is that one not working? There. Almost symmetric. So I was trying to make it at least look symmetric in my picture. I guess I could have just held it down, but we have this symmetric thing. So I'm going to point out by symmetry, once I can draw it symmetrically, that the y bar should be 0, because with respect to the y-axis, the x bar, sorry, should be 0, because there's the same amount of mass on the left-hand side and the right-hand side. But what do we have now for our region? This is going to be, and then of course we also have this in there too. So this is y equals 0, and this is y equals 9 minus x squared. This tells us that this is type 1 region. I have -3 is less than or equal to x is less than or equal to 3, and 0 is less than or equal to y is less than or equal to 9 minus x squared. So I have a type 1 general region. And so the first thing that we get is the mass is the double integral over the region D of just rho xy dA, which is the integral from -3 to 3, the integral from 0 to 9 minus x squared of y dy dx. This is equal to, oh, I'm going to have to FOIL out a bunch of stuff. Okay, this is the integral from -3 to 3 of 1/2 y squared evaluated from 0 to 9 minus x squared dx, which is going to equal the integral from -3 to 3 of 1/2 times 9 minus x squared dx minus 0, which is equal to 1/2 the integral from -3 to 3 of 81 minus 18x squared plus x to the 4 dx. Now I want to use a clever trick that you're supposed to remember from 115, but this is an even function. I'm sorry, plus negative x to the 4 is equal to 81 minus 18x squared plus x to the 4, which is f of x. So it's an even function. And then that says if you're even by the symmetry of this, basically, because it's an even function, same as the picture over here, it's not the same function, but because of this symmetry, I can say that this is 2 times the integral. I don't want to put negative 3 in there, so I'm just being lazy. This is 1/2 times 2, the integral from 0 to 3 of 81 minus 18x squared plus x to the 4 dx. So that one was just because I'm simply lazy, and then the 1/2 will cancel, and I don't have to put negative 3 in there anymore. And that's the only reason I did it. This is equal to now 81x minus 18 over 3x cubed plus 1 over 5x to the 5, evaluated from 0 to 3, which is equal to 81 times 3 minus, what do I get? This would be 6 times 27 plus 1 over 5 times 243. And then let's find out where this is. So this should be equal to 243 minus 162 plus 243 over 5, which is 81. I'm going to have to multiply that by 5 plus 243 over 5, which is 405 plus 243 over 5, which is some horrible number, 648 over 5. I picked these arbitrarily. I didn't realize the numbers would get so nasty. I won't make sure the fractions are that bad on your midterms, etc. So that's the mass. Notice that this gets a lot. There's, for this, the planar ones, there's 3 double integrals we have to compute. In general, for the solid regions in 3 space, this is 4 triple integrals we're going to have to compute. So now, yeah, this is a symmetry. My, the moment about this with respect to the y-axis is going to equal 0 because of symmetry. I just noticed right out the gate. But if you don't notice that, it's also going to have to equal the double integral over the region D of x rho xy dA, which will be equal to the integral. I can still set it up for you. Integral from negative 3 to 3, the integral from 9 to 9 minus x squared of x times y dy dx, which is equal to blah, blah, blah. You get 0. But by the symmetry, before I even started, if I'm trying to find the center of mass with respect to the y-axis, it's going to be the same on both sides. There's the same density, and so everything's going to be the same on both sides. With respect to the x-axis, it will not be the same. Plus, I'm lazy and I don't want to do the calculation. Mx, on the other hand, is not going to be 0. Mx is the double integral over our region D of y times rho xy dA, which will be the integral from negative 3 to 3, the integral from 0 to 9 minus x squared of y squared dy dx, which now becomes even, I hope again, the integral from negative 3 to 3 of 1/3 y cubed evaluated from 0 to 9 minus x squared dx, which is the integral from -3 to 3 of 1 over 3 9 minus x squared cubed dx. We just did the squared one, so we have 9 minus x squared times 81 minus 18x squared plus x to the 4, which is going to equal 729 minus 9 times 18x. That should be a squared. I'm trying to cheat by copying and I can't even. That should be a to the 4 minus 81x squared plus 18x to the 4 minus x to the 6, which is, long story short, my bracket wasn't big enough. I'm just doing the foiling calculation for you so that you have it. This is 729 minus 243 x squared plus 27 x to the 4 minus x to the 6 is where I'm getting that. So this should equal the integral from -3 to 3 of 729 minus 243 x squared plus 27 x to the 4 minus x to the 6 dx. This again is even, luckily, because all the powers are even. And so I can luckily write this as 2 times the integral from 0 to 3 of 729 minus 243 x squared plus 27 x to the 4 minus x to the 6 dx. That should be, sorry, I lost my 1/3. There's a 1/3 on the outside there. Which is now equal to 2 over 3 times 729x minus 243 over 3x cubed plus 27 over 5x to the 5 minus 1 over 7x to the 7, evaluated from 0 to 3. It's going to be some hot mess. We're going to get equals 2 over 3, 3 to the 5 minus, this ends up being 3 to the 3 times 3 to the squared, which is going to cancel. That's nice. 27 over 5. 3 to the 5 minus 1 over 7. 3 to the 7. So these ones cancel outright. And I get, oh, I see. I'm going to write this like this. 2 times 3 to the 6 times 3 over 5 minus 1 over 7. You'll see why I did this, because I have to write this as mx over m, the mass, to get the center of mass, which is 2 times 3 to the 6 times 16 over 35, getting the common denominator, which we can also write as 3 to the 6, all right? 16 is 2 to the 4, so that should be 2 to the 5 over 5 times 7. You'll see why I did that in a second. That says, therefore, that was the calculation of our 3 triple integrals. This says x bar is going to be my over m, which was 0 over m, which was 0. And more importantly, we have, where was, oh, I see. So y bar is equal to mx over m, which was 3 to the 6 times 2 to the 5 over 5 times 7. And then if you look at 648 over 5, that's upside down. That's going to be 5 over, we get 3 to the 4 times 2 to the 3. which now you can cancel a bunch of stuff off. In particular, the 5s will cancel out, right? I'm just going to look at the prime factorizations. You can simplify the numbers however you want. So this says x bar, y bar is equal to 0, 36 over 7, which should be this guy. I think it should be somewhere right here. So it should be way higher up, but then it should be symmetric with respect to the y-axis. Note to self, those were even simple integrals, but these integrals can get long and nasty and the numbers can get horrible. Okay, let's do application 4, moments of inertia. Again, in 3 dimensions, this will get more complicated because there's rotation and all kinds of stuff in about planes, etc. But we'll get at that when we get the triple integral. All right. Again, I'm not explaining all the physics, inertia, and all this kind of stuff, but we're going to assume that we're just going to have to compute double integrals. So 1. The moment of inertia about the x-axis. Or remember, this is y equals 0. This is going to be ix, unfortunately, which will be a double integral over the region D of y squared times rho xy. And the second one, the moment of inertia about the y-axis, which is actually x equals 0, is going to be equal to iy, which is the double integral over the region D of x squared rho xy dA. So moments of mass, mx and my, multiplied by y and x respectively. Moments of inertia now are going to multiply by y squared and x squared respectively. And then the third one, the moments of inertia about the origin, they call it. Is going to be I0 is Ix plus Iy. All right, what example? We're on example 3 or 4, I think. 4. So let's do a calculation about this. Example 4, let's find compute Ix, Iy, and I0 for region D in the first quadrant. bounded by y equals x squared and y equals 1 if our density rho xy at each point in the region is given by the product of the coordinates x times y. What do we want to do? Always draw a picture if you can, I guess. It helps a whole lot to find your bounds and decide what kind of, eventually in 3 dimensions, this gets harder and harder to sketch and draw, but you want to look at the idea or get the hints on whether you want to use polar coordinates in the 2-dimensional case or cylindrical and spherical coordinates, etc., in the general case later on. All right. So when I draw this, it said bounded by the parabola y equals x squared and y equals 1. And we want to go from here to here, y, and x is going to go from 0 to 1. So this is a type 1 region. 0 is less than or equal to x is less than or equal to 1. And we're starting at x squared and moving to 1 in the y. Therefore, Ix is equal to the double integral over our region D of y squared times rho xy dA. These integrals are going to feel awfully symmetric because it's just our rho is x times y. So one of them will be x times y, x squared, and one will be times y squared. So they're going to look awfully similar. This is equal to the integral from 0 to 1, the integral from x squared to 1 of xy cubed dy dx, which is equal to the integral from 0 to 1 of x over 4 y4 evaluated from x squared to 1 dx, which is equal to the integral from 0 to 1 of x over 4 times 1 minus x to the 8 dx. Now we're just cleaning that up. This is the integral from 0 to 1 of x over 4 minus x to the 9 over 4. I write this backwards. Yeah. Sorry, I just have a typo in my now. I have to look. So it should be, yeah. Yeah, that's right. Which is now what? This is equal to 1 over 8 x squared minus 1 over 40 x to the 10 evaluated from 0 to 1. Why do I have those backwards? I have one backwards which says blah 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 1/10. I might have a mistake in there. If you find the mistake, let me know. I only have 20 minutes left. I want to do high. I might have a typo there. I'm not sure. I have a negative problem, but I'm going to guess it's 1/10, so I'm just stealing. I cheated. Iy is the double integral over our region D of x squared times rho xy dA, which is again the integral from 0 to 1, the integral from x squared to 1 of x cubed y dy dx, which is going to equal the integral from 0 to 1 of x cubed over 2y squared from x squared to 1 dx. This is the integral from 0 to 1 of, now we're going to get x cubed over 2 minus what are we going to get? X, so x7 over 2 dx, which is now going to equal, yeah, I had a typo in the last one because this one looks correct, which is, at this stage, it's just integrating polynomials, and I'm lazy because it's the morning and it's the second class I've already taught this morning. So now this is the integral from, or sorry, I can compute the antiderivative. This is going to be 1 over 8 x to the 4 minus 1 over 16 x to the 8 evaluated from 0 to 1, which should be blah, 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 1 over 16. And then finally, if they want I0, which would just be Ix plus Iy, is going to be 1 over 10 plus 1 over 16, which is 13 over 80. So now those are the mass density and charge density. And then from mass density, we can also do mass, center of mass, moments of mass, moments of inertia. That was just the same. Okay, before I end today, I want to make sure I do surface area of double integrals. So eventually, probably in the review for the midterm or whatever, etc., I'll do more application double integrals with all of these guys. But the major applications that I did again are charge density, and then we have mass density, moments of mass with center of mass, and then moments of inertia. So let's do the last thing in the chapter in the Stewart calculus, I think, is surface area as a double integral. I think we did surface area in 115 and Mat 115. We would do surface area as a single integral by taking the arc length and then rotating it around, and so we can get surface areas of certain things. Now we can actually look at the surface as a function of two variables and use double integrals is the idea. So let's try to draw this in a fancy. If I have something like this, and then it's over a rectangle. And then we subdivide it up. So we chop this up and we get a regular region, etc. What we're going to do is below this region somewhere is going to go up to a small region in my surface, which is going to have at the point, actually, we're going to find a tangent plane, which is going to approximate, this is like linear approximation and multivariable from 214, hopefully, but we find a tangent plane, Tij, or that little area is going to be the area of that parallelogram in the tangent plane is going to be roughly approximately equal to the small area in the surface, because this is our surface S. And then we have this region R, and then we're going to have this small delta A. And so what we're going to do is, for the long story short, D is subdivided, and this gives small subsurface areas of S given by delta Sij. So on the actual surface is the orange part. We're going to approximate it by the green part, which is underneath the red part. This is what's happening. And this is approximated, which is approximated with the area of the parallelogram delta Tij, the green guy, on the tangent plane. To f of xy at point xi star ij star. So we subdivide it, we pick a sample point in each of those things. Above that sample point is a point on the surface. That point on the surface has a tangent plane. The area of the parallelogram determined by the partial derivatives vectors in there. We didn't do tangent planes. That was in 214. But when we do all of this stuff, we have this tangent plane and approximate this. And then so what we have to do is derive the area of that parallelogram. Remember, delta A is delta x times delta y always. And then the area of this parallelogram, what we're going to have is these two tangent vectors essentially. And then that's the area delta Tij is the area of that thing. And then we're going to have these two vectors A and B. So what that tells us is the approximate surface area over D is given by the sum from I equals 1 to n, the sum from j equals 1 to m of delta Tij, because each Tij approximately equals the actual delta Sij. So what is Tij? It's moving pretty fast, but what we're doing is, again, we're starting with a rectangle. We want to know what the exact surface area is with this double integral. So we subdivide the rectangle into pieces just like we did to find double integrals. Then what we're going to do is we want to know what the actual surface area is. So we pick a sample point in the rectangle. Above that sample point is a point f of xi star yj star in our surface. At that surface, there has to be a tangent plane or a linear approximation in the two-dimensional sense for this point. And it gives us a tangent plane to the surface at that point. And then it'll be a plane which touches at one point, which is approximately equal. And then we find these small tangent vectors, which give us a small area of a parallelogram in the tangent plane, which will be approximately equal to this surface area guy. So what is this Tij? We have to use linear algebra. Cross product, etc. Delta Tij is equal to, if you have two vectors A and B, it's equal to the norm of the cross product of A and B. But A is equal to, when we look at this, delta xi plus 0, times j plus delta x fx, the partial derivative, times the vector k. And b in the other direction, when we look at this, is no component of the I direction plus delta y times j plus delta y times fy times k. Therefore, A cross B is equal to I j k, the 3 by 3 determinant where I put this in here. Now I get delta x 0, delta x fx and then I get 0 delta y fx or fy, which is equal to, when I get this final vector, this is negative delta x delta y fx, comma, negative delta x delta y fy, comma, delta x delta y. I have this in all three coordinates, so I can scalar multiply this out using scalar multiplication. This is equal to delta x delta y times negative fx negative fy 1. And that tells us that the norm of this is equal to the norm of delta a times negative fx negative fy. Fx and fy are the partial derivatives of the function of two variables, fx, y, which is going to equal, I can take delta a out of the norm, and it's positive, so it stays, absolute value can go away. Negative fx, negative fy, 1. How do I take the norm of a vector? I take the square root of the square of the sum of, or the sum of the square of its coordinates, which is going to be delta a times the square root of fx squared plus fy squared plus 1 squared. And I don't write the 1 squared. This says, or delta tij is equal to the square root of fx squared plus fy squared plus 1 times delta a. That was what we wanted from linear algebra. Oh, somebody must have asked about cross product in the class last time. So the area of the surface is equal to the limiting process of this, but long story short, this is equal to the double integral over our region D of the square root of fx squared plus fy squared plus 1 times dA. That's the formula that we want to compute surface area as a double integral. Yeah, let's do something fairly tame. How much time do I have left? I have like 8 minutes. So example 5. Find the area of the surface z equals x plus y squared lying above the triangle with vertices, they give me 0, 0, 0, 1, and 1, 1. All right, let's draw a picture of this. They give me the point 0, 0, 0, 1, and 1, 1. So this is the triangular region D. So this is going to be type 1. This is y equals x, and this is y equals 1. Actually, let's do it the other way. Let's do a type 2 region for once. I probably did this in the notes last time just because everyone was asking, is it always going to be type 1 region? It's like, no, I can set it up as type 2. In this case, it's invertible, so I can set it up as type 1 and type 2. I think the calculation becomes slightly easier too. So this says 0 is less than or equal to y, and 0 is less than or equal to x is less than or equal to y. So y is between 0 and 1, and x is between, I'm going this way now, x is going from 0 to y. My function, first of all, crash course in partial derivatives, f of xy, which we call z, was x plus y squared. So the partial of z with respect to x, which is fx, is equal to, I hold y constant, and we're just going to get 1. The partial of z with respect to y, which we call fy, is equal to 2y. And so this says fx squared is equal to 1 squared, which is 1. This says fy squared is equal to 2y squared, which is 4y squared. You have to calculate the partial derivatives of the function now. So that tells me that the square root of fx squared plus fy squared plus 1 is equal to the square root of 1 plus 4y squared plus 1, which is square root of 2 plus 4y squared. Therefore, that tells us that the area of the surface is equal to the double integral over a region D of the square root of fx squared plus fy squared plus 1 dA. It's nice to regurgitate that definition every time so you don't need the formula on an exam, and then you get everything right. I just chop up and I've computed everything I needed first. Now I can just put it in there. So this is equal to, I found out what my region was. It was type 1. I'm going to go from the integral from 0 to 1. The integral from 0 to y of, now you can see why I did this, I think, first, because we're going to get the square root of 2 plus 4y squared dx dy. If I did dy first, I would have that nasty business outside, and then I would have to use trigonometric substitution for something horrible. It could be done, but I don't want to. So this is going to equal the integral from 0 to 1 of the square root of 2 plus 4y squared y dy when I compute the antiderivative of the first one. Which is, now I can use a substitution. This is y equals 0 to y equals 1. So I have let w equal 2 plus 4y squared. Then 1 over 4 dw equals y 1 over 8, sorry, y dy. And I have to change my bounds. When y is 0, this says w is equal to 2. And when y is equal to 1, this says w is equal to 6. So I have to change my bounds. This tells me I get, this is equal to the integral from w equals 2 to w equals 6 of w to the 1/2 times 1 over 8 dw, which is equal to 1 over 8 times 2/3 w to the 3 over 2 evaluated from 2 to 6, which is equal to, what do I get? 1 over 12, 6 to the 2, 3 over 2, minus 2 to the 3 over 2, which you can leave like that, I guess, or you can put it fancy if you want. This is 6 root 6 minus 2 root 2. Some horrible number. I think we'll end there. So this is surface area. I'll do another surface area, at least one next time, and then we start triple integrals over boxes, and then triple integrals over general regions. It will get crazier from there. Triple integrals over general regions, there's going to be 3 types of general regions. So we'll get to that on Thursday. Yeah. 1 over 10 is correct. Yeah, okay. Usually I steal them from books or make the calculation ahead of time so that my calculations are right. It's just somehow in my type when I was writing it down, I had a negative somewhere wrong, but 110. Okay, good. Thanks. I'll see you next time.